Title: How engineers designed a panoramic gantry elevator. With a FAMM pit, how can a glass panoramic elevator be installed near a villa balcony with only a FAMM pit? At first, this sounds like a design question. The homeowner wants a beautiful glass elevator. The elevator should match the villa. The shaft should look open and elegant. But in real projects, a panoramic villa elevator is not only about appearance. It is also a structural, electrical, mechanical, maintenance, and safety engineering project. A villa elevator project in Malaysia shows this clearly. Project background. This project was for a 2-story villa in Malaysia. The client wanted a glass panoramic elevator installed near the balcony area. The preferred structure was a traction gantry elevator, selected for stable operation and comfortable ride performance. But the site had 3 major constraints. First, the foundation could not be dug deeper than FAMM. Second, the local power grid supplied FAV. Third, the balcony area did not have clear and solid top fixing points. So the challenge was not simply to install a glass elevator. The challenge was to make the elevator fit the real site conditions, without asking the client to make major changes to the villa. Challenge fit. The FAM pit. The first issue was pit depth. A standard traction gantry elevator often requires around FAM to FAM of pit depth, depending on the structure and configuration. But this project only allowed FAM for a gantry elevator. The bottom frame is important. It affects mechanical clearance, structural support, installation accuracy, and long-term stability. If the bottom frame is too tall, the elevator cannot fit the available pit. If the mechanical footprint is compressed without proper design, reliability may be affected. In this project, the gantry bottom frame was redesigned, and the mechanical footprint was compressed. This allowed the elevator to be installed within the FAM pit, while maintaining a 5 kg load capacity and face operating speed. The important point is that shallow pit design should not mean simply reducing safety space. It requires structural redesign and engineering verification. Challenge FAV power supply. The second issue was electrical. Many home elevators are commonly designed around FAV or FAV power, depending on the market and system type. But this project required operation under FAV, using standard electrical components, under unsuitable voltage conditions can create problems such as electrical instability, control faults, overheating, or long-term motor damage. So the control system needed to be adapted to the local power condition. For this project, a custom voltage stabilizer was integrated into the control system. The goal was to support consistent operation under the local grid condition and reduce the risk of electrical instability. This is an important reminder for villa elevator projects. Power supply should be confirmed early, not after the elevator design is finished. Challenge FAV balcony top fixing points. The third issue was structure. Panoramic elevators near balconies often look visually light, because the glass shaft is transparent. But the structure still needs reliable support. In this project, the balcony area did not have clear and solid top fixing points. For a traction gantry elevator, upper support is important for frame stability and long-term operation. If the top fixing points are uncertain, the elevator cannot simply be installed based on appearance or position preference. The solution was to design custom mounting brackets and reinforce the upper support system. This helps stabilize the glass shaft and secure the gantry frame. For balcony side elevator installations, the best-looking location is not always the easiest structural location. Engineering review must come first. Maintenance design. The project also focused on reducing maintenance effort. The elevator used self-lubricating guide shoes, which reduced the need for manual oil refilling. It also used permanent magnet synchronous gearless motors for both the main drive and the door operator. Gearless motors reduce the need for gear oil changes and can support quieter operation. For a villa elevator, this matters because the elevator is close to daily living areas. The system also included Smart Eco mode. When the elevator is idle, cabin lights, fans and displays turn off automatically. When the elevator is called, the system reactivates. This helps reduce unnecessary energy use during long idle periods. Safety system safety was also part of the design. The elevator included an ARD or automatic rescue device. During a power outage, the ARD activates automatically. It moves the elevator to the nearest floor and opens the doors so passengers can exit safely. The system also included a one-touch emergency call function. For home elevators, especially in villas, emergency safety should not be treated as an optional feature. It should be designed into the system from the beginning. Conclusion: this Malaysia project shows a simple but important lesson. A panoramic villa elevator is not only a design feature. It must solve pit depth, structural fixing, voltage stability, maintenance needs, and emergency safety at the same time. In this case, the solution included a traction gantry panoramic elevator, a redesigned bottom frame for a Fei-mem pit, Fei kg load capacity, Fei speed, adaptation to Fei-P power, custom top fixing brackets, self-lubricating guide shoes, PMS gearless motors, smart eco mode, ARD rescue, and one-touch emergency call. For more details about this Malaysia panoramic elevator case, you can read the full project article here. https EKCNE lift, Fei panoramic elevator, Fei pit Malaysia, case